So it's not, there we go. Okay. Alrighty, so it seems like for the most part things with the exam went well. I was a little bit slow in posting the password to Canvas. I know that caused some stress, but everybody who emailed me got a response right away, and I think it looks like everybody was able to get in and complete things. Before we pick back up and start going into new material, are there any deep concerns or questions about the test? Anybody have trouble getting their work submitted to me one way or another? I know some folks had trouble on Canvas. I got a few via email, and if you emailed something to me and I sent something back to you, then we're all good to go. But does anybody have any concerns about the test or protocols yesterday that we would like to sort out or talk about before we start back with our work on polar coordinates? If you don't feel like talking out loud, of course, you can always send me an email or a Canvas message, or you can chat to me privately here. But if you did have any problems with the test yesterday, if you were unable to get in or you had time issues or anything like that, it's important that you talk to me right away. I'm willing to work with you guys. I know that this is a difficult setting to work in, and I don't want to make it any harder than it needs to be. So we're in this together. If there's anything that you're concerned about, please, please, please reach out to me, talk to me. We'll take care of it. It's going to be okay. When we left off, we talked a little bit about how to go back and forth from polar coordinates to rectangular coordinates and rectangular coordinates to polar coordinates. I want to kind of remind you the basics that we went through there, and then we're going to start looking at graphs. So the last two topics in this class are polar coordinates and parametric curves. So we're going to be exploring those topics a little bit. Damn, all these markers. So I'm going to be cycling through markers. I am pretty much out of working markers at this point, but hopefully I'll be able to get something reasonable for you guys. There is going to be a new homework that opens up, but it's not going to be due until next Monday, so don't panic, and it's not going to be super long. It'll be on the stuff that we were talking about just before the test, and a little bit of more challenging extensions of that stuff. So I'll just kind of remind you what we've been doing. We've been looking at polar coordinates. And the basic idea there is that you have a pole and a polar axis. And if you want to locate a point that you might have previously thought of as being in the XY plane, instead of presenting with coordinates X and Y that tell you how far to go over and how far to go up, like we normally would, we present with an angle, theta, and a distance, r. So this point, which has Cartesian coordinates x, comma, y, would have polar coordinates r, comma, theta. To me, it's always been more intuitive to think of doing theta first. And depending on what resources you learn from, it seems like most folks, when they're just getting used to polar coordinates, prefer to think of starting like this, pointing out, rotating theta, and then walking out r. But another option is to go out along this polar axis to r, and then rotate up theta. One of the reasons I prefer to think of theta as happening first is because when we get to graphing, most of the functions we're going to graph have the independent variable theta and the dependent variable r, meaning r is given as a function of theta, like r equals 2 cos theta, or r equals sine theta times 7. And so it's more convenient to think of theta as changing and watching how r reacts. I think I posted to you guys modules, the polar graphing paper which you might want to print or sketch or something like that to play around with if you use a note-taking app. Download the PDF, and you'll find it very useful when it comes to graphing points. And then later, definitely when it comes to graphing functions. The trick to going back and forth from one coordinate system to the other is the following set of equations. First, r squared is x squared plus y squared. And you can see that from a little right triangle that you could draw in here. Then from that same right triangle, we get the three relations: x is equal to r cos theta, y is equal to r sine theta, and the tangent of theta is y over x. I know that we did a fair amount of this before, but since this week is the first time I'm going to be requiring you guys to do it in the homework, I would like to practice just swapping 1 or 2 points. Maybe 1 point in one direction and another point in the other direction, from polar to rectangular and rectangular to polar. And then we're going to look at some more graphs. So the very last thing we did before the exam was to look at the graphs of r equals a constant and theta equals a constant. So swapping coordinate systems. There are some important facts to remember, like every Cartesian point, x comma y, has one and only one representation. If I tell you the coordinates, x and y, you know that point. And if you hand me the point, you could tell me the coordinates. There's only one way to write each point. But in polar coordinates, every point has infinitely many representations because of the 2 pi periodicity of theta. If you rotate around 2 pi, of course, you come back to the same point. But then there was also this issue of r being negative, reflecting you through the origin. So really, there's kind of like 2 infinite families of representations for each point. Still, if I want to convert a rectangular coordinate, and I'm going to abbreviate rect chord to try and save my crappy markers, point. So the normal xy point, let's go with about 2 comma negative 1 into polar coordinates. The first thing we should do is graph the point. Let me see where it is. Let me get some intuition. So I just draw the picture. Doesn't have to be big, doesn't have to be fancy. I come out here to 1, 2 along the x-axis. I come down to negative 1 here along the y-axis. And there's my point. So I'm looking for this r. And I could think of theta as being measured from the positive x-axis like this. Or I could think of theta as being measured in the negative direction, down. Either one is going to be okay. And to make my life a little simpler, I think I might prefer to measure theta like this. So if this is the point whose x-coordinate is 2 and whose y-coordinate is negative 1, then I can find theta and r using those equations. R squared equals x squared plus y squared. Well, x is 2, so that's 2 squared, plus y is negative 1, so that's negative 1 squared. So r squared is equal to 5. 2 squared plus 1, which means that r is either the square root of 5 or r is the negative square root of 5. And associated with each choice is an infinite family of representations for this point. Normally, we like to take r being positive, and we like to pick theta to run from maybe 0 to 2 pi, or negative pi to pi. Here, what's going to be most convenient, because I have this last relationship, tan theta equals y over x, that's negative 1 over 2. So the tangent of theta is negative 1/2. And since I've chosen to measure theta negatively like this, rather than measuring the big angle that goes all the way around, the inverse tangent of -1/2 will actually be this theta value. So as I've drawn it there, that's theta. It's one of the reasons it's nicer to choose to measure theta down like this rather than all the way around like that, because the inverse tangent function will only ever split things up that are between -π/2, which is down here measured in that direction, and +π/2, which is up here. Sorry, I just got a message in the chat. All right, so in order to find this theta, I need to calculate the inverse tangent of -1/2. I know that this is going to be the angle between -π/2 and +π/2, so the tangent of that angle is theta. So the tangent of that angle is -1/2, which is what I want. So I open up my calculator, and I ask for the inverse tangent of -1/2, and that's -0.464 radians. So one polar representation for this point is the same as the polar coordinate point. So just to be clear, this is x and y, and over here, this will be an r and a theta. √5, comma, -0.464. So I thought it worthwhile to go through just one of these really quick. We should check whether this theta value makes intuitive sense to us. Is this a negative theta? Yeah, it's being measured down from the positive x-axis. Is the size about right? Well, you know, pi is like 3.14, so π/2 is like 1.5. So this is considerably smaller than π/2, which puts us in that quadrant. So yeah, everything here makes sense. Questions on going from Cartesian coordinates to polar coordinates? Okay, let's do an example where we go back the other way. So I give you the polar coordinates for a point, and then ask you to come up with the Cartesian coordinate. So convert the polar coordinate point to Cartesian. Right, and let's use the point r comma theta equals, let's do something weird. How about a radius of -2 and a theta of -π/3. So just like when I'm going from Cartesian to polar, the first thing I should do is plot the point. When I'm going from polar to Cartesian, the first thing I should do is plot the point. But how do I plot a polar point whose radius is negative? So first, let me be clear. Let's graph it. And you go, well, but r is negative. How do I draw that? To which I would say, first graph the point with the positive radius, 2, -π/3, then reflect through the origin. Right, so this is the easiest way, I think, to wrap your head around what goes on when r is negative. So if r is negative, just first pretend like it's not. First deal with the same point, but with r positive. And then to go from this point to this point, you'll reflect the point through the origin. So if I want to graph 2, -π/3, I would rotate down pi over 3, and then go out 2. So this is the polar point 2 comma negative pi over 3. And so the point that I actually want, negative 2 comma negative pi over 3, is this guy reflected through the origin. So module my bad art. Here it is. And it's going to take time for you to build this intuition. So looking at these coordinates and immediately saying, oh yeah, that's a quadrant 2 point. I think that's something that's only going to come after you practice for quite a while. And the particularly challenging thing is dealing with the negative radius. So remember, this is the approach. First graph the positive radius point, and then reflect it through the origin. Now actually finding the x and y coordinates isn't terribly bad. X is going to be r times the cosine of theta, which is negative 2 times the cosine of negative pi over 3. The cosine of negative pi over 3 is negative 1/2. Negative 2, so I'll write it out. This is negative 2 times negative 1/2, which is positive 1. Oh no, negative pi over 3, sorry, cosine of negative pi over 3. Cosine of negative pi over 3 is positive 1/2. So this is negative 2 times positive 1/2 is negative 1. And the y coordinate is r times the sine of theta, which is negative 2 times the sine of negative pi over 3. The sine of negative pi over 3 is negative root 3 over 2. So this is negative 2 times negative square root of 3 over 2. So negative times negative makes positive. The 2's cancel, and you just get the square root of 3. So the Cartesian coordinates, x and y, for this point are negative 1, comma, square root of 3. X, and that's y. And that makes sense, right? If I look at this point right here, I would believe that this is negative 1 and that this is the square root of 3. First, the signs are correct, right? It puts us in the correct quadrant. Secondly, the sizes, the relative sizes make sense from the picture. Here, the y coordinate looks like it's definitely larger than the x coordinate. And I know that square root of 3 is larger than 1. So any questions on this example where we go from a polar coordinate point to the Cartesian coordinates? Everybody see everything okay? Okay, as long as we're all still feeling comfortable with how to do this, then I would like to look at some examples where we're graphing functions. We looked at some basic functions. For example, we saw that the equation r is equal to a constant gives a circle centered at the origin of radius that constant. So like r equals 2 is the circle centered at the origin of radius 2. The unit circle, which has a fairly complicated equation in rectangular coordinates, becomes a constant function. One of the important tricks for understanding what's going on in polar coordinates is to try and imagine what happens to very simple equations when you apply the polar coordinate transformation. What I mean by that is the fundamental idea, or the idea that to me is most fundamental, that keeps things straightest in my mind, is to remember that vertical lines, like y equals a constant, those get turned into concentric circles. And horizontal lines, like x equals a constant, those get turned into rays emanating from the origin. So the basic graphs we've looked at so far are equal to a constant. These are all going to be circles centered at the origin. Right, examples here are like r equals 1. This is the unit circle. Because if you plot in polar coordinates, treat this like a function, right? I'm thinking for every value theta, r is equal to 1. If you make a big table, a theta comma r table, then the r equals 1 equation, no matter what theta you plug in, always spits out 1 for r. So when theta is 0, r is 1. I'm writing this in polar coordinates, r comma theta. It just looks the same as the Cartesian coordinate here. When theta is pi over 4, r is still 1. When theta is equal to pi over 2, r is still 1. And no matter what you plug in for theta, this equation, r equals 1, is always going to return 1 for r. So for example, when theta is equal to pi, r is still 1. So over here we have the polar point 1 comma pi, because you rotate pi and then walk out a distance of 1. So the first coordinate constant, r constant, instead of being a horizontal line, is now a circle centered at the origin. The other kind of basic graph we looked at is theta equal to a constant. So for example here, if I look at the line, I shouldn't say the line, if I look at the function or the equation, theta equals, let's say pi over 6. Think of this as being like the same as x equals 1, right? It's a, or y equals 1, and this being the same as x equals 1. Constant functions. Here, if I were to build a table and see how theta changes with r, this says no matter what r is, theta is always going to be pi over 6. For example there, then I would have the point 1 comma pi over 6. I would also have the point 2 comma pi over 6. And I would have the point 3 comma pi over 6. I could look at the point -1 comma pi over 6. So it's just like when you were learning to graph basic equations in your very first algebra class. We're just plotting points. And you can see that if I connect all these points, you can make as many of them as you want, I'll get this straight line. It's a line passing through the origin. So theta equals constants. These are all straight lines. Passing through the origin. So in Cartesian coordinates, x equals a constant is a vertical line, y equals a constant is a horizontal line. In polar coordinates, r equals a constant is a circle centered at the origin, and theta equals a constant is a straight line going through the origin. What we want to do as we move deeper into chapter 8 is to get comfortable graphing more complicated polar equations. Usually we're going to think of them with theta as the independent variable and r as the dependent variable. So just like normally we graph functions where y is a function of x, most of the time here we will be graphing functions that are more akin to this, where r is a function of theta. Questions on these two examples or the basic idea of graphing polar equations? it feels weird at first. So it's okay if you have questions. I want to talk about it. And I know that you're kind of trying to change gear coming out of that test. So what are we thinking? The tactics and strategies are very much the same as they are graphing functions in the XY plane. We're making tables, right? If R is always 1, then I could build a table and plug in a whole bunch of different theta values, and R would always be 1. And that gives me these points. If theta is pi over 6, then I could make a big table and plug in a whole bunch of different R values, but theta never changes with R. Theta is always pi over 6. So the theta value in those points on that table would always be pi over 6. And then we just connect those points with a nice smooth curve. But just like when you start graphing in your earlier algebra classes, at some point, you want to have a higher level perspective. Like when you look at the graph, or you look at the equation y equals x squared, you know that's a parabola. And if you look at any other quadratic equation, you know that that's going to have the same basic shape. So you want to start building up libraries of functions like that in the polar setting. And these are the first two kind of families. R equals a constant, circle centered at the origin. Theta equals a constant, straight line through the origin. A very natural question to ask is, well, so if that's a circle centered at the origin, can I center circles in other places? So can I start taking equations whose Cartesian graph I know and transform those into polar equations? Because then I will know what those polar graphs look like. Going the other direction, I think from a different perspective, instead of saying the graph is the foundational thing, I'm going to start with a function whose graph I know and then figure out what its polar equation is. You could start with some basic equations involving the polar variables and see what their graphs look like. And I think the first thing that we should do as we move away from this is that second one. So let's see if we can't sketch a graph, sketch the polar graph R equals 2 cos theta. Since this isn't a constant function anymore, I am going to actually write out the table. We can go through that process. And then we'll plot each of the points that we get from every row of the table. And then we'll connect them with a nice curve, just like you would have in college algebra on your very first day. Here, R is given as a function of theta. So I think of theta as the independent variable and R as the dependent variable. So I'm going to plug in a bunch of theta values and see what R values I get out. So I plug in 0, then pi over 6, and then pi over 4, and then pi over 3, and pi over 2. And now I'm going to start taking larger steps. From there, we'll go to pi, and then 3 pi over 2, and then 2 pi. That should be enough for me to at least get a good feel. When theta is equal to 0, R is 2 times the cosine of 0. Cosine of 0 is 1, so R there would be 2. When theta is equal to pi over 6, the cosine of pi over 6 is the square root of 3 over 2. 2 times the square root of 3 over 2 is the square root of 3. When theta is pi over 4, cosine of theta is root 2 over 2. 2 times root 2 over 2 is just root 2. When theta is pi over 3, cos theta is 1/2 times 2 is 1. When theta is pi over 2, the cosine of pi over 2 is 0, so R comes back into 0 here. And then we take a big step. We go from pi over 2 all the way to pi. The cosine of pi is -1. So between theta equals pi over 2 and theta equals pi, R goes from 0 to -1, or sorry, -2. 2 times cos pi. And then when theta is 3 pi over 2, the cosine of 3 pi over 2 is again 0. And the cosine of 2 pi is the same as the cosine of 0, so we will have come all the way back around to 2. So each of these gives me a polar point. Before I start plotting those polar points, any questions about where that table is coming from? Okay, so I'm going to start by plotting the polar point with theta equals 0 and r equal to 2. Really, when we write these, we always write r first. So this would be the polar point 2 comma 0. This would be the polar point root 3 comma pi over 6, and so on. So when theta is 0, I haven't rotated at all, and I need to go out 2 units. Let's call that 1, let's call that 2. Here is where I'm starting, the first point from my table. Then if I rotate up to pi over 6, r will have come in just a little bit from 2 to the square root of 3. You can check in your calculator, square root of 3, about 1.7. So if this is 2, then 1.7, r value would be here, and then I rotate up by pi over 6, which is about here. So there's that second point. If I continue rotating up to pi over 4, then we come all the way into root 2. Root 2 is about 1.4, so he's going to be somewhere right around here. And then I keep rotating. Once I get to pi over 3, or to r has come all the way into 1, so I come out here to 1, and I rotate up to pi over 3, which is about here. And I will get this point. So that's these first 4 points plotted. When theta has rotated all the way up to pi over 2, r has come all the way into 0. So if r is 0, we're at the origin. And as I let theta rotate past that, towards pi here, r comes all the way out to -2. So before I plot that point, I think maybe it would be worthwhile to come back to my table. This is the first place we're going to start encountering negative r values. Let me add a few more subtle theta values in here. You can already see a shape taking form, but we're not sure. Is it going to continue like this? Is it going to continue like this? Is it going to spiral out? Who knows? So let's look maybe at theta equals 3 pi over 4 before we look at theta equals pi and 3 pi over 2. When theta is 3 pi over 4, the cosine of 3 pi over 4 is negative root 2 over 2. Multiply that by 2, and you get negative square root of 2. And then here we have -2, and then 0. So this next polar point I'm going to plot is going to be negative root 2, comma, 3 pi over 4. And this is where things get a little bit tricky. When r is negative, remember you have to reflect that point through the origin. Well, over here I don't want to clutter up my picture too bad, but I am going to draw the polar point root 2 comma 3 pi over 4 without the negative, and then reflect it through the origin just once to get a feel for what's going on. So if I go out to root 2, which is like right about here, and then I go up to 3 pi over 4, that would put me over here. So I need to reflect that point through the origin. So let me draw it here. Here's root 2, and then 3 pi over 4 is this angle over here. So if I rotate that guy all the way around, I'll be somewhere right around here. So this is the polar point, square root of 2, comma, 3 pi over 4. That's about right. So then to get my point from this point, I need to reflect this point through the origin. So the next point on our graph is him reflected through the origin. That's ugly. Here. Okay. That good? That's good. Symmetric, maybe a little further. Don't need to be too picky. Here, about here. Can you start to see what shape this is going to be? Pi comma negative, or negative 2 comma pi. Well, I start with positive 2 comma pi. And I reflect it through the origin. That'll land me back here. The shape of this graph is a circle. It just kisses the origin here. I'll make that clear. My art is just bad. It's a circle centered at the Cartesian point 1, 0. So this point isn't on the graph, that's just the center of the circle. And the tricky bits are graphing the portions where r is negative. And the key is to graph the positive r version of those points and then reflect through the origin. So this guy is a circle centered at the rectangular point at the xy coordinates 1, 0 of radius. Well, what's the distance from that center to this point? That's the distance from 1, 0 to 2, 0. So radius 1. So take a second, make sure you get this into your notes. And I want you to think about where each of those points is coming from and if there's anything that feels weird to you or anything you'd like to talk about a little bit more. Any questions on this guy?
Could you, it says a circle centered at, does that say XY equals something?
Yeah, xy equals 1, 0.
1, 0. Okay, thank you.
Yeah, at the point 1, 0. And I'm writing the xy to emphasize that that's the Cartesian coordinates, not the polar coordinates. Although, ironically, the polar coordinates for that point are the same. Other questions or thoughts on this guy? If you don't have questions for me, I have questions for you. What happens if I change the 2 to a 3 or a 4? What do we think r equals a times cos theta looks like in this setting? I know if I graph y equals a cos x, that's a cosine wave with amplitude a, right? No horizontal or vertical shifts. What do we think that family of functions looks like in the polar setting? So more generally, if I look at r equals, I'm going to write it as 2a cos theta, because here you notice the radius is half of the number that was in front. And the center is along the polar axis or along the x-axis at a over 2 also. So all of these polar curves are circles centered at the Cartesian point x comma y equals a comma 0 of radius a. So this whole family looks like that. If I asked you to graph r equals 16 cos theta in polar coordinates, you would know that that's a circle of radius 8 centered at the point 8 comma 0. Does this make sense? Any questions on this?
Is something like tangent going to be different?
Say that again?
Is something like tangent going to be different?
Tangent's going to be very different. If you swap the cosine for a sine, we'll see that the shape of the graph doesn't change, but the location of the center of the circle does change. So I'd like to do that as our next example, if that's okay. But then, yeah, if you were to look at, honestly, off the top of my head, I don't think I've ever graphed r equals tan theta in this setting. It might be a fun thing to do. But I've got a couple other examples to look at first. Yeah, swapping the cosine for a tangent, though, will change things dramatically. Swapping cosine for a sine, though, doesn't change things too bad. And the relationship between them is actually a fun thing to discover. So next, let's look at r equals maybe 6 cos theta. Yeah, that was a really good question. That was from Ryan, right? If we swap the cosine for a tangent, what happens? I would be curious to see. But we have precious little time here, so I do need to cover some other examples. But maybe that would be a fun thing to explore just a second after class. So let's try sketching r equals 6 sine theta. Let's see what swapping cos for sine does. I can make my table again. There's no harm in doing that. There will be a faster way to get some of these graphs. And when we move on to the pedal graphs, which are the next family of examples I wanted to look at, I will show you something that's a little bit quicker than just drawing the table. Now, I'll pick the same sort of theta values, so we'll do 0, pi over 6, pi over 4, pi over 3, pi over 2. And then we can jump a little bit to 3 pi over 4. And then we'll go to pi, and then 3 pi over 2. And we'll see if we can't have a clear picture of what this thing looks like by then. So now when theta is 0, r is 6 times the sine of 0 is also 0. When theta is pi over 6, r is 6 times 1/2, which is 3. When theta is pi over 4, I have 6 times root 2 over 2, which is 3 square roots of 2. When theta is pi over 3, the sine of pi over 3 is root 3 over 2. So that will be 3 times the square root of 3. When theta is pi over 2, the sine of pi over 2 is 1. So this will output r equals 6. When theta is 3 pi over 4, the sine of 3 pi over 4 is the same as the sine of pi over 4. So this will also be 3 times the square root of 2. When theta is equal to pi, the sine of pi is 0. So r will be 6 times 0 is 0. And when r is 3 pi over 2, theta sine of 3 pi over 2 is -1. So this will be -6. Good. Looking good. Okay. So let's go ahead and start plotting these points. We start at 0, 0, right? Theta is 0 and r is 0, so that's keeping me at the origin there. I might need a little more space here. As theta rotates up from 0 towards pi over 6, r is growing from 0 all the way out to 3. So if I come up here, I guess I need to pick some sizes. Let's do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So if I rotate up 30 degrees to pi over 6, I need to walk out 3 units, or I can walk out 3 units, 1, 2, 3, and then rotate up 30 degrees, putting me about here. So this is the point 3 comma pi over 6 in polar coordinates. I rotate up a little more to pi over 4, and r goes out from 3 to 3 times the square root of 2. Square root of 2 is like 1.4. So this is a little bigger than 3. If we want a decimal, it's about 4.24. So I'd walk out here 1, 2, 3, 4 1/4, and then rotate up pi over 1, 2, 3, 4 and a quarter, and then keeping that radius fixed, rotate out to pi over 4. So something like this. So this is 3 root 2 times pi over 4, or comma pi over 4. And then I rotate up to I rotate up to pi over 3, and r's gone out even more to 3 times the square root of 3. So pi over 3, and then walking out a little further, looks like this. So this is the point 3 root 3 comma pi over 3. And as we keep going out, we got all the way out to pi over 2. Then r has jumped up to 6. So here is 6 comma pi over 2 in polar coordinates. I can see that my art is off a little bit. Rotating past pi over 2 to 3 pi over 4, now coming all the way over here. This is the 3 pi over 4 line, right? Theta equals 3 pi over 4. I need to walk out along that line 3 times the square root of 2. So that's the same distance. This is going to be a symmetric point with that other guy. So this is 3 root 2 comma 3 pi over 4. Can you kind of see what shape is going to be filling in here? If we go all the way out to pi, we're back to 0. So through this first bit, we're sweeping something out that looks like this. I'm going to adjust my art a little bit here to try and make things look as they should. Okay. So modulo my bad art, modulo my bad drawing. You can see that the shape here is again going to be a circle. This is a circle centered at the Cartesian point, or the rectangular point, x comma y equals, the last one was centered on the x-axis, this guy is centered on the y-axis. That's what swapping cosine for sine does. So this guy is centered at the point 0, comma 3 in the xy plane, and he's of radius 3. So we've got these two families now. The curves r equals 2a cos theta and are circles of radius a centered at a comma 0, centered at the Cartesian point xy equals a comma 0, and r equals 2a sine theta. This family of curves are circles centered, sorry, we did the radius first last time. So these are also circles of radius a centered at the Cartesian point x comma y equals 0 comma a. In other words, swapping sine for cosine or cosine for sine rotates things 90 degrees. It's things 90 degrees clockwise, counterclockwise, going cosine to sine. So these are our first two kind of more interesting families. These equations are circles centered on one of the coordinate axes. Let's see. If I changed one of these to a negative number, does this rule still work? So if I took all of these guys, if I wanted to graph r equals negative 6 sine theta instead of just r equals 6 sine theta, what's that going to do to this picture? Well, I'm swapping all of these r values for their negatives, which would mean reflecting each one of those points through the origin. So this point, for example, would get reflected down here. This point would get reflected over here. This point would get reflected over here. If you swap that 6 for a negative 6, then you're going to get a circle down here. Symmetric to this guy, the same as this guy, just flipped over like that. Similarly, if you swap the constant in front of your cosine for a negative, you're going to reflect all of those points through the origin, which is going to just flip your circle's center over to the other side. Do we feel comfy with both of these graphs? So I would like to do one more example with you guys today, and it's a little bit more complicated. The other two kind of big families of graphs that we're going to talk about, at least immediately, are cardioids and petal graphs. So circles are nice and simple in polar coordinates. That's one of the reasons we like polar coordinates, and that's one of the reasons they're so important in physics in places where you're dealing with radial symmetries, because circles have very simple graphs, or very simple equations in polar coordinates. Other things which have simple equations in polar coordinates are heart-shaped graphs. So imagine you indent the circle a little bit. I just poke the circle in on one side, and it'll kind of turn into a bloopy shape, like a heart. We call those cardioids. Think like cardiac, heart-shaped. The other family that we're going to meet, and the next example that I'm wanting to do for you guys today, maybe we should do the cardioid first, maybe that's a little easier, are graphs that look like flower petals, lots of little bloops coming out. I think maybe the cardioid is an easier way to introduce the more sophisticated graphing system. So what we want to do is start moving away from having to make a table for everything. It's nice to get to know families of curves. That can save us from having to make a table. But there's one other kind of strategy, and it's the last thing I want to show you today. And that's to first sketch the curve in rectangular coordinates. So sketch the sine wave or the cosine wave in rectangular coordinates, and then try to move that graph over from rectangular coordinates to polar coordinates one point at a time. It can go a little bit faster, than making the table. So for our cardioid example, yeah. Let's look at r equals 2 plus 2 cos theta. What I'm about to show you was very hard for me. What we've been doing so far was very hard for me when I learned it. So if it feels weird to you, I'm sympathetic, and I'd be happy to talk to you about it and take some time. The trick I'm about to show you is what made it finally click for me. So instead of trying to jump straight to a polar graph, like making a table and have the first picture you draw be the polar graph, first sketch this in rectangular coordinates. So in other words, if I look at this as my theta axis and this as my r axis, and I treat those like I normally treat x and y, then I definitely know how to graph this, right? This is a cosine wave. It's got amplitude 2, it's been shifted up 2. Draw this a little bigger. And I need some more space up above here. So if I come up here to 1, 2, I'll draw in my equilibrium line. 3, 4. And now I just draw the regular cosine wave. I draw a cosine wave, amplitude 2, shifted vertically up by 2. That looks like this. Start coming back a little sooner. All right. So this is my horizontal axis is theta, my vertical axis is r, and this is my normal cosine wave. So this is 2 pi out here, 1 full period, because it's just cos theta, the period is 2 pi. So we'll go through 1 full cycle. By the time we get out here to theta equals 2 pi. And then you want to label all of the kind of interesting points along this graph. So that's any mins or maxes, anytime you go through equilibrium. So I'd want to know what is this point? What is this point? What is this point? what is this point, and what is this point. And then I'll transfer the graph over all at once into the polar setting. So if this is 2 pi, then this is pi. This guy right here, where cosine comes through its equilibrium, is pi over 2. And then this point up here, of course, is 0, 4. Did I label this one? This is 3 pi over 2, 2. All right, so that is the rectangular coordinate graph of that function. If I gave you y equals 2 plus 2 cos x, that's what you would draw. Now I want to transfer this picture over into the polar setting. It can be a little bit tricky, but I think once you master this, you'll be a lot more comfy graphing in polar coordinates once you master this technique. I like to think of there as being an arm swinging around here, and a little dude with a marker or something walking in and out on that arm. So the arm just swings around, and that's theta, right? That's theta going around. So here's theta equals 0, theta equals pi over 4, theta equals pi over 2, theta equals 3 pi over 4, theta equals pi. And as that arm swings, I got a dude running in and out along it, drawing the curve. So I begin out here. Here, I can actually stack some markers together and construct the arm for you. Right, here's my swinging arm. It's going to rotate around. And as it rotates around, I'm just going to track where r goes. So we start, theta equals 0, r is 4. Let's call this 4. So here's the polar graph. And we start at the polar point 4, 0. So now theta starts to increase. My arm starts to move around. What's happening to r as theta starts to increase? Well, r is decreasing, right? Which means this guy is walking in along the arm. By the time I get to pi over 2 up here, my guy is halfway in on this arm. So he starts out here, and as the arm rotates, he walks in, he walks in, he walks in. Now I'm approaching that equilibrium point, pi over 2, 2. Here's theta equals pi over 2, and r is 2. So here is that point, 2, pi over 2. But much more importantly, if you understand that rotating and walking in process, you can see what the whole curve in between here looks like. I'll do my best. I only have 2 hands. So as this rotates around, my dude is walking in. So I get something like that. Okay. Something about like this, getting me to this point. And now that arm is going to keep rotating around past pi over 2 until I get to pi. And by the time I get to pi, my little dude has walked all the way in. R is now at 0. So what's that mean? Well, here it is, rotating, rotating. R is coming in, R is coming in, R is coming in, R is coming in. You can see the shape, right? My little dude walks in as theta rotates around, and I get this. So now we are here at 0, pi. So theta is at pi, and r, my dude, is all the way at r equals 0. He's not out along the arm at all. But as we start to rotate past pi, as this arm continues to swing around, what's happening? Theta starts to come back up. And by the time I get to 3 pi over 2, he's back to halfway out the arm. So we get here to this polar point 0, pi, and then we rotate past that and we get to this polar point 2, 3 pi over 2. Can you see the heart shape for me? So far we have traced this portion. Now, as theta continues to rotate past 3 pi over 2, my dude's going to start walking back out on the arm. And what we're going to get, I'll just draw it here. It's going to look like this. And it looks like a heart, which is why it's called a cardioid. So this thing where you imagine the theta arm rotating around and the guy walking in and out along it in order to generate the graph is the most useful tool for me in sketching these graphs. And it was the thing that finally made me able to go from that graph to this graph quickly. But it's not going to happen on its own. It's not going to happen without a lot of practice. So as you work through the new WebAssign homework this week, I really want you guys to be drawing the graphs by hand. It's not the same to just pick the graph from the collection of 4 or whatever that WebAssign gives you. It's imperative that you go through this process of sketching the rectangular coordinate graph and then transferring it over into polar coordinates. So again, we call this a cardioid because it's heart-shaped. And then we want to start asking the questions, well, what happens if I play around with those constants, the way I play around with the constants in the other examples? You know, changing the 2 to a 6, or changing sine, cosine to a sine, or what if I change one of those 2's to a 4, but I leave the other one a 2? What effect might that have on the graph? You can start to imagine the effect it'll have on the polar graph by first thinking about the effect it will have on the rectangular graph. So right now we have 2 plus 2 cos theta. If I change that first 2 to a 1, that drags the rectangular graph down by 1, which means that part of it is going to dip below the x-axis. What that's going to correspond to over here is the creation of a little loop inside the heart. So when this guy dips below the x-axis, that will correspond to a little loop here. Another fun game to play is to like shade a portion of the rectangular graph in a different color and see if you can find the corresponding portion over here. So the part that I just shaded blue there corresponds to the part that I'm shading blue here. If this dipped beneath the x-axis, if I move this whole thing down by 1 so that a meaningful chunk of this blue part was below the x-axis, that would correspond to some of these points needing to be reflected through the origin, which is going to put them over here in quadrant 4. And all in all, it's going to generate a weird little loop inside there. So instead of having the pointy heart, you have a pointy heart shape with a little loop inside. So I know it's the day after a test, and probably everybody is feeling a little bit burned out, but I want to hear what you're thinking, because I also know that this isn't super easy stuff to absorb, and I don't want to dump too much on you at once. What are we wondering about as we look at this? Okay, okay. Then I will go ahead and show you one of those pedal graphs. We're a little bit short on time, but we got enough time to do one more of these. So let's do one of the simpler ones. Let's look at r equals, I'll leave it a cosine, but let's make it a cosine of 2 theta. And we're going to sketch this the same way we sketched this one. First, we're going to draw in rectangular coordinates. And then using that metaphor with the rotating arm, we're going to transfer that rectangular coordinate graph into a polar coordinate graph. So r equals cos 2 theta. This is a regular cosine wave, but now the period is changed. Instead of having period 2 pi, it just has period pi. In other words, the frequency is twice as fast as the regular cosine. So I'll mark this here as 2 pi. You always want to sketch your rectangular coordinate graph at least from theta equals 0 to theta equals 2 pi. You need to get a picture for what happens as that arm rotates all the way around. So even though the period here is pi, I'm still going to graph it all the way out to 2 pi. So if that's 2 pi, this is pi. I'll mark this as 1 and this as -1. So we need to go through one full cosine cycle. From there to there. And then we go through another full cosine cycle. There. All right, so here's a quick and dirty sketch of cos 2 theta. Just like before, we want to label all the important points. So any mins, maxes, or equilibrium points. Those deserve to be labeled. So this is 2 pi comma 1. This is pi comma 1. And this is 0 comma 1. This is pi over 2 comma -1. And this is 3 pi over 2 comma -1. And then we also have these equilibrium points here, 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 and here. This first guy occurs halfway between 0 and pi over 2. That's pi over 4. 2 pi over 4, this is 3 pi over 4. 4 pi over 4, this is 5 pi over 4. 6 pi over 4, this is 7 pi over 4. So there's my nice rectangular coordinate picture with all of the important stuff labeled. And now I will transfer it over into a polar graph. I begin at the polar point where theta is 0 and r is 1. So I'll call this 1. And this is my polar point, theta equals 0, r equals 1, which, remember, we always put r first, is 1 comma 0. Now, as I rotate up from theta equals 0 to theta equals pi over 4, my little man walking along that arm has to go all the way out from 1 to 0. So my little dude, as I go from here to here, has to run all the way in. Like that. And that creates this nice kind of loopy shape. So right here is the polar point 0 comma pi over 4. And as this arm rotates back out past pi over 4, r becomes negative. So this is where things get a little bit tricky. If r was positive, then I would be walking back out along this arm and drawing something that looked like this, as theta goes from pi over 4 to pi over 2. But r is negative, so I have to reflect each of these points through the origin. So this point would get reflected over here, this point would get reflected over here, this point would get reflected down here. And what I actually end up drawing is another, a little too big, another similar looking loop, but down here. Try my best to make this look nice. Yeah. My art is bad and I feel bad. There we go. And we finish at this point whose polar coordinates are -1, comma, pi over 2. And I think you start to get a feel for what's going on. So the part that I've just traced is coming from this blue part of the rectangular graph. Because this guy is below the horizontal axis here, r is negative, this piece of the graph ends up reflected through the origin from where we would think it is based on the rotating arm scheme. As we rotate past pi over 2, r starts to come back in. So r went all the way out to -1, but now it's going to start coming back in. If it was positive and coming back in, if r was positive and coming back in as we rotate from theta equals pi over 2 to 3 pi over 4, we would get something that looks like this. So we have to take this whole thing here and reflect it through the origin. That's going to give me something like this. Now, as we rotate past 3 pi over 4 towards pi, r becomes positive again. So now I'm looking at this part of the rectangular graph here. R is 0 at 3 pi over 4. And as I rotate past 3 pi over 4 towards pi, r is going to come out to 1. So here we are. We're rotating past 3 pi over 4, and r is growing, and we get all the way out here to the point, the polar point, 1 comma pi. As theta rotates past pi, my little dude starts running back in along his arm. And that's going to draw this shape. So now I've just sketched this part between theta equals pi and theta equals 5 pi over 4. As theta goes past 5 pi over 4, normally I would be drawing down here, but r is again negative. So what I'm going to get is not this, but this reflected through the origin, which is this. And then as I come past this point right here, which is -1 comma 3 pi over 2, this polar point. So normally theta equals 3 pi over 2 would have me down here. Here's 3 pi over 2 comma +1, reflect it through the origin, and you get theta equals 3 pi over 2 and r is -1. As we come past 3 pi over 2, r starts coming back in towards 0. That means I'm going to come back into the origin, and then rotating past 7 pi over 4 to 2 pi, r grows back out to +1. There's a bunch of weirdness here. And so I've tried to kind of drop this bomb slowly, but sketching these graphs is a little bit tough. In particular, if I gave you the finished picture, it can sometimes be very, very hard to answer the question, well, what's the range of theta that's associated with this blue arc? This looks like it's between theta equals, I don't know, 5 pi over 4 and 3 pi over 2, because it's in the second half of quadrant 3. But really it came from theta equals pi over 4 to pi over 2, because r was negative, and I ended up reflecting through the origin. Ooh, excuse me. Sometimes having a really good polar grid to draw on can make learning this stuff easier. I'm working on a blank board, but that polar graphing paper, and I'll double check, I'm pretty sure I posted it to Canvas under the modules last week. I'll make sure it's there. That polar graphing paper can make things a lot easier, especially as you're just getting used to it. So I really do encourage you to consider printing or downloading and playing with that polar graphing paper. I also posted some videos from Patrick JMT on graphing polar graphing equations in polar coordinates. He goes through a number of examples like this, and seeing more examples can only ever help. After we play around with this stuff a little bit more, we're going to talk about parametric equations, and we'll talk a little bit about sequences and series before the semester ends. but we're more or less through the bulk of it now. So breathe easy. I will get your exam one grade, or sorry, exam one. I'll get your exam 3 graded and back to you as quickly as I can. The way I've been doing these online things, I take the scans that you sent me, I read through your work, and I grade those as the free response. As I read through your work, I will write lots of comments, which I will then scan and upload under the feedback in Canvas. So when you go to the gradebook, there's a little option to add comments. Once you see your grade in the gradebook for exam 3, click on the comments, and there will be a link there to take you to a scan that has all of the notes I would normally write on the test itself. Questions about where we are, what we're doing? All right, I'll go ahead and pop that new web assigned homework. It's going to be all this polar coordinate stuff and a little bit of some parametric equation stuff that we haven't talked about yet, but we will talk about tomorrow and Thursday. And that is it for now. I will see you guys tomorrow afternoon. Oh, 15 question on web assigned for exam 3 was a full exam. No true, false, multiple choice. No, so the web assigned portion is going to be graded as the true, false, multiple choice, and the work that you uploaded to Canvas is what is graded as the free response. So that's it, that's the whole test. What is the point at the top? The coordinates up here are -1, r is -1, and 3 pi over 2. Theta is 3 pi over 2. So this is the polar coordinate, -1, comma 3 pi over 2. Other questions? All right, then that's where we'll leave it for now. I've been recording these on my local computer, so give me a little bit of time to process it and get it uploaded to YouTube. But for my calc class, the YouTube stuff has actually started working and working well. So I am going to make that switch. All right, if there aren't any other questions, then I will see you guys tomorrow afternoon. Okay, have a nice afternoon, guys.